day, grade 12 learners. Welcome to today's mathematics lesson. My name is Anelen Sindane. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono, Discovery Center, and broadcast by Pagama Research and Development. Our lesson for today is differential calculus, and we are going to focus on the subtopic first principles and rules of differentiation. You will realize that differential calculus in our paper 1 has 35 plus minus 3 marks. It's a lot of marks. And the subtopic has about 12 plus minus 3 marks. So you will realize that we need these marks in order for us to do well in our paper 1. At the end of the lesson, we should be able to determine the formula for first principles using average gradient. We should be able to differentiate specified functions using first principles. We should understand the concept of a limit as it is used in our formula for first principle. We should also differentiate using the rules of differentiation or rules of a derivative. You will see as we go along these rules coming up. Now we can refer to our CAPS document as well as our examination guidelines. We will need this knowledge. We need functional notation. We need the knowledge of average gradient. I hope you remember this one. We know that our gradient is given by m is given by y2 minus y1 over x2 minus x1 from our analytical geometry. But now we are going to be looking at average gradient as we will be dealing with curves and functions and no longer ordinary straight lines. Algebra will need knowledge of our algebra, knowing the use of our distributive laws as we do that, as we substitute and simplify. We also need our algebra, knowing how to collect like terms, how to simplify fractions, and so on. You will need lots of that. And then we also need our laws of exponents to simplify some of the expressions before we are able to apply the laws of differentiation. Now, if you are given a curve like that, and we can tell that this is the function f of x is equal to x squared, and you are given those 2 points, and the coordinates of the points are our x value is 2 and our y value is 4, and the other point our x value is 3 and our y value is 9. Now we want to find average gradient, so we will just draw a straight line and find the gradient of the line that is joining those 2 points. Because it's average, it's not the exact gradient. So hence we change the naming there as average gradient. So to get our average gradient, we know we can use the y value when our x is 3 using functional notation, that is f at 3 minus f at 2, which is the y value when our x is 2, and we substitute our x2 minus x1, which are those values, and we are able to get our gradient given as 9 minus 4 over 3 minus 2, and our average gradient will be 5. Remember, this is an average gradient. It's not the actual gradient between those 2 points. Remember, this is a straight line drawn to just connect those 2 points, and we are able to find the gradient of that particular line. We move on. Now, the formula for calculating average gradient, we will just make a bit of change on the formula for gradient, as you will see here. So we just calculate the gradient of the line connecting the 2 points, and we get our average gradient as given there by the formula. It's f at x2 minus f at x1 over x2 minus x1. Remember, you can change this. You can write it as well as f at x1 minus f at x2, and you also change the order for the denominator. It becomes x1 minus x2. It's not always that you use the x2. You can swap around as long as you maintain the order on the numerator and denominator. Now, we have our function y is equal to x squared, and we are having 2 points, P and Q. I can say now the distance from x to the second point, x2, I will name it. So our x1, we can say this is x, and then we say our x2 becomes x plus h. So you are adding a distance from that point so that you are able to get point Q with coordinates x with an x value x2, which is x plus h. Then from there, we are able to still use the formula for average gradient. Our f at x2 becomes f of x plus h, which is the y value when our x is x plus h. And the original point P will have coordinates x, and the y value becomes f of x. Using that, we are able to find the average gradient between P and Q using our formula. In place of x2, we are going to substitute x plus h, and that becomes f of x plus h. And in place of x1, we substitute x, and we are able to get our average gradient formula as f of x plus h minus f of x divided by x plus h, which is our x2, minus our x1, which is x. And you will realize that on the denominator, the x values are going to give us 0 plus h, and our denominator becomes h there. Now, you will realize that if we make this distance h, for example, if our h is there, you are able to see that our point x plus h becomes closer to x. And if we keep on reducing the value of h, reducing the value of h, we will end up having the distance h approaching 0. And we are going to introduce the concept of a limit there. We can reduce that distance, bringing it closer and closer to that point x. We will end up having the distance h approaching 0. It will be negligible. But we are not saying h is equal to 0. It's approaching h. We are bringing it closer to that point P, meaning that the point that we are looking for average gradient ends up being a single point. And we will be calculating gradient, for example, at point P, and our x value plus 0,000 something, it becomes almost the same as finding the gradient at point P with our x value being x. Now, if you check on this side, I have given a illustration that, for example, if our x value at point P is 1, it means now we are able to find the gradient at point P where our x value is 1. And we are going to use our first principle where we are saying if we reduce the size of our h, we end up being able to find the gradient at a point instead of finding the average gradient between 2 points, because that distance, as we reduce it, becomes so small that it ends up being a point instead of it being 2 separate points that you can distinguish. And that will lead us to a formula where we say if our function is f of x, f dash of x becomes the limit as h tends to 0 or approaches 0. It will be given by f of x plus h minus f of x all over h. This formula will lead us to what we call the finding the derivative from first principles, as you will see as we move along. Now, I've used 1 plus h to illustrate that if our x value at that first point is going to be 1, and the distance between the first point and the second point is h, the second point will now have the coordinates as 1 plus h, and the y value there becomes 1 plus h squared. So, using the coordinates of those 2 points, we are able to find the average gradient of those 2 points, and we are able to substitute into our formula, and we simplify that, and we end up getting, if we expand 1 plus h squared, remember 1 plus h squared can be written as 1 plus h multiplied by 1 plus h, and we did this in grade 9 and grade 10. We need this algebra a lot as we move along. You can see the simplification of our expression. We get 1 plus 2h plus h squared minus 1. If you check, we have like terms there. 1 and negative 1 will give us 0. We end up remaining with 2h plus h squared. From there on, there's something that we can do there. If you look at h, we can factorize the numerator, and after factorizing the numerator, h on the numerator and h on the denominator will give us 1. We will need this concept as we move along. So we are able to say now the average gradient will be given by 2 plus h. But remember what we have said. As h becomes small, the average gradient will approach a particular value, and that value becomes the limit. As you can see, we are able to draw a tangent. Remember the definition of a tangent. It is a line that intersects or touches a curve at only one point. In this case, because that point, which is where our x is equal to 1, we are able to find the tangent at that particular point, because that is the point of intersection, and the gradient becomes the gradient at a point of intersection between the curve and the tangent, which is a straight line. And we should be able to get the equation of that particular tangent. Now, so to find the gradient at a single point, we are going to use this first principle. And we know the symbol now, it's given by the limit. You are able to see that above that limit, there is an h and an arrow, meaning we have a value which that particular function is approaching. In this case, h approaches 0, in which case we know that as h approaches 0, our x value will approach 1 as well. And we know that the limit for that particular function will be 2. In some instances, we are using 2h sorry, it's 2 plus h as our limit. So when we want to evaluate the limit, I know some we are taught to substitute whatever the value we have as being approached there, but the correct way is to investigate what happens as h approaches 0 from the left as well as approaching 0 from the right. And then we are able to see that this limit will also approach this value of 2. But I know we're told, so once you are evaluating, some are able to do that. But remember, once you substitute whatever the value that is being approached, you no longer write the term limit. You will see as we move along. So our solution there means 2 plus 0 will give us 2. The meaning of this is the value of the first derivative as h approaches 0 will be 2 for this particular function when our x is equal to 1, isn't it? So we will move to the next part. I want us to investigate the concept of a limit. Now, as I have indicated, if f of x is a function defined for all x values, we know that as x tends to a, or as x approaches a, from both the left and from the right, f of x tends to a particular number. And we are going to say that becomes the limit for that particular function. And as you can see, f of x tends to a number, say b, then that limit of f of x as x tends to a is going to be b. We write the limit as x tends to a of f of x is equal to b. Or we use the other notation where we say f of x approaches b or tends to b as x approaches a or tends to a. Now, just to have an idea of how we evaluate the limit, though it's not a major part, we just need to understand how this limit works so that we are able to use it for our first principles. If you look at the first example, we are having the limit and our function is x squared minus 2. We want to evaluate the limit as x approaches 3. Now, as I indicated, the correct way is to substitute the values of x that are less than 3 and the values of x that are closer to 3 on the right hand side. For example, on the left hand side, you can say your x is equal to 2,95. And then you make x closer to 3, you substitute, for example, 2,995. You compute this on your calculator. X equals 2,99995. You will see that the answer that you get there, it's closer to 6, but it's below 6. And then I say you also substitute some of the values into the function that are bigger than 3. For example, you have 3,001. You substitute 3,0001, 3,00001. You will realize that as you substitute into that x squared minus 2, the value becomes either it's greater than 6, but it will be 6,000000, so that when you try to round it off, it will give you that 6. Even from the left, if you keep on substituting your 2,95, 2,9995, 2,9995, when you try to round off the answer that you are computing on your calculator, it will round off to a whole number, for example, 6 in this case. So, to try and evaluate a limit, we can now substitute 3 instead of x, and then we evaluate the value when we substitute that particular number that we are approaching. In this case, the limit will be 6. So we write this as the limit as x approaches 3 on a function x squared minus 2 will be equal to 6. That is the correct way of doing it. Now, if you look at the second example, we are having x squared minus 9 over x minus 3. We want to evaluate the limit as x approaches 3. If I use the last part that I did where I said we stop writing the term limit and we substitute the x value into the function, you will realize that if I substitute on that function, I will end up having 3 squared minus 9, over 3 minus 3. And you are able to see that the denominator becomes 0, and we cannot have a fraction, evaluate a fraction where the denominator is 0. So it means when we need to evaluate a limit, we need now to first of all do something that we did some time back. You are able to see that you can factorize this. You will get x squared minus 9 is a difference of 2 squares, which will give us x plus 3 and x minus 3 as factors. And you will realize that x minus 3 is the same as the other factor. We realize that those will cancel each other and give us 1, and we will only remain with an expression that is now can be written as x plus 3. From there on, we are able to do what we were able to do on the first example, where we take the limit value, in this case, which is 3, we now substitute it into the function, but we no longer write the limit as x approaches 3 because we are already evaluating the limit, and this will give us an answer of 6 as well. I chose these two deliberately so that we are able to just understand how the concept of a limit works. You will realize this when you are working with first principles, where we have our f dash of x as h approaches 0, given as f of x plus h minus f of x over h. What I was explaining just now is to show you that in this kind of a definition, you cannot substitute your denominator as 0 because the whole fraction becomes undefined. Hence, we need to understand how we evaluate this limit so that we do not just say we substitute for whatever we have, but we must investigate what happens as h is approaching whatever value that we are having there. In this case, it's 0. And if we just substitute 0 into this formula, it becomes undefined. But we know that this should work because we are making h as small as possible, but we are not making it to be exactly equal to 0. As we know in mathematics, we cannot divide by 0. Now, I will give you tips of how the first principle works. We must know the definition. And remember, we are not always dealing with f of x. It can be g of x. It can be y equals. We know the different notations that we use for functions. If your function is h of x, it means the definition of first principle becomes the limit as h tends to 0 of f as h of x plus h minus h of x, all this over h. If your function is g as well, it means you are going to have g of x, g dash of x is equal to the limit as h tends to 0 of g of x plus h minus g of x, all this over h. It doesn't mean that you will always be working with f of x, but on our formula page it is given as that. We should always refer to our formula page as it assists us as we move along. Now, for us to evaluate, we need to compute and simplify our f of x plus h first in our function. For example, if they said evaluate the first derivative from first principles of g of x is equal to x squared as an example. Let me use 3x squared. So what does that tell you? It means we must first of all evaluate g of x plus h. So it means where there is x, we should substitute with x plus h. So this becomes x plus h squared, and we have our coefficient 3 there. And we should simplify this separately before we can substitute back into the formula. We substitute the expression for f of x plus h and f of x into the definition, then we simplify. So the choice is ours, or we can simplify the expression of f of x plus h and f of x, then we substitute the simplified one into our definition. It's up to us, you will see as we move along. We avoid substituting h is equal to 0, but we check what happens to the expression as h becomes smaller. I have explained this part, that in our calculus, our notation has to be on point, otherwise we will lose marks if we make the mistake that others make, where they write the limit h approaching 0, then they substitute h equals to 0 into the function, and that becomes wrong. So we should avoid doing the substitution, but we know what happens as h tends to 0 there. Now, I want us to look at the example. I'll write the definition for you, and we are going to work out one question where we are given our f of x as 5. So, using what I have explained, step number 1, we need our definition. It's already written on the left hand side, as you can see. Our function f of x is given as 5. Our function f of x plus h, what should I write there? We indicated we need knowledge of our functional notation or function notation. What should I write? What should I write? Our function is f of x is equal to 5. What should I write as f of x plus h? I know you have decided wherever you are. You will find out that f of x plus h will also be 5. Because if we are to draw this function, it is a horizontal line where you are having your, this is our f of x or our y values, and those, and here we have our origin, and those are our x values. So we are saying This, you can write its equation as y is equal to 5. It's a horizontal line. So whether you're going to the left or to the right, that equation, any point that lies on that line will be y is equal to 5. So whether you are going to the right, if your h is positive, it will always be 5. Whether you are going to the left, where your h is negative, it will always be on that line where we have our y is equal to 5. Now, we can now write down and we compute our f of x plus h will be 5 like that. Now, let's substitute our f of x plus h back into our formula and we see what is going to happen. So we will get our first derivative given as that. And then from there, we are able to simplify. So we've done substitution. We simplify, we get 0 over h. If our numerator is 0, 0 divided by anything should give us what? 0. I'm not saying I will substitute h there as 0. I'm saying the fraction is 0 over h. When I simplify this fraction, I get 0. That is why there I will have my first derivative as 0. Are you able to see that? And then from there, we have managed to evaluate our derivative from first principles when our function is 5. This one, because there is not much that we have done in an exam situation, it will have 3 marks or 4 if the examiner is lenient, but there is not much that we have done here, so we will get our solution as that. Let's look at another type of a function where we should use first principles to find the derivative. We have our f of x as 3x plus 2. We evaluate our f of x plus h and we get this as 3x plus h plus 2. We simplify this. Our f of x plus h will be given by 3 times x. We are distributing the coefficient 3, which is outside the bracket. We get 3x. 3 times positive h, we get positive 3h. Then we write plus 2. That is how we simplify our algebraic expressions using the distributive law. You are able to see that that is the expression that we get. We can now take this and substitute it back into our definition. You are having the definition of first principles. We substitute and get f of x plus h minus f of x over h. We are going to substitute. This is our f of x plus h. We substitute it back into the formula. That's our f of x plus h. Minus f of x, that's our f of x. We divide that by h. We simplify. We know that if that one is, so on our numerator, we are going to have our limit as h approaches 0. We are going to have 3x plus 3h plus 2. Negative times 3x, we get negative 3x. Negative times positive 2, we get negative 2 all over h. 3x minus that will give us 0. 2 minus 2 will give us 0. So we are left with 3h over h. And we know that h and h are like terms. That would mean that h and that h are going to give us 1. Hence, our limit becomes as h approaches 0 will be 3, and we know that our first derivative in this case will be given as 3. I know you have done this at school. We move on to the next example. If our f of x is x squared in this case, I will give you a chance to work out some. These ones, we are going to do them together so that we get to know what we are expected to do as we move along. I will follow the steps. The first part, our definition, we know it. We evaluate f of x plus h as I have indicated. So x plus h, f of x plus h. Where there is x, we substitute x plus h. Our function is f of x squared. So we will square that, and we know that this will give us x plus h and x plus h. You open two brackets if you are having challenges of expanding our binomials. So this will give us x squared. This multiplies that. This multiplies that. It will give us xh. This multiplies that. It will give us xh. So we will have 2xh. And then h times h will give us h squared, which is what we have up there. We take these now. We substitute them. It is important that you always write the formula because writing the definition has a mark. But as we mark these scripts, you will find some of the learners move the equal sign to be between the limit and that. So please avoid that mistake. You cannot change the definition. You have to use it as it is. You don't have to try and make changes there. You do your substitution, you work. Your limit must always be there until you evaluate your limit, then it disappears. Then you have your first derivative. So I have substituted that on the numerator. That's our f of x plus h. That's our f of x. You will realize I have x squared there and I have x squared there. X squared minus x squared gives me 0, meaning I'm now left with 2xh plus h squared all over h. And then I'm now able to evaluate the limit. I'm able to see that there is a common term there, h. So h and h are going to give us 1. That h and that h give us 1. And then we are left with our function as 2x plus h. And then we evaluate our limit and get our derivative as 2x. So in an exam situation, you will get your expansion of f of x plus h. You will substitute, you simplify. So that mark, either you'll get it up there or you'll get it when you do the substitution into the definition. And then you'll get a mark for simplification, and you will have 1, 2, 3, 4, 5 marks for finding the first derivative from first principles. In this case, you will realize that if f of x is x squared, our first derivative becomes 2x. We move on now. If our function is 2x cubed, this one is going to give us a headache, but according to examination guidelines, we must know how to find the first derivative from first principles of a function that has our x as cubed. We do have our f of x, and we know that our f of x plus h would become, we have our coefficient 2, we substitute in place of x, we put x plus h, and that to the power 3. And we know that this is the same as saying 2 into x plus h, x plus h, x plus h. Then you take two brackets at a time to help you simplify this. Otherwise, it can give you a headache if you try to do it without following our ways of simplifying algebraic expression. So we'll expand the first two brackets, then you distribute the other bracket, and then you distribute the 2. You will get, in the bracket, you'll get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then from there, we distribute the 2 so that we get 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed. Our definition of first principles, we have it there. We substitute into the formula. We simplify to get 6x squared h because 2x cubed is the same as 2x cubed. Because you are subtracting, that will give us 0. They will disappear. And then from there, we take out a common factor h, and then we remain with 6x squared plus 6xh plus h squared. And then you investigate what happens as h tends to 0. You will substitute your h as 0 somewhere to evaluate without the term limit, and you will see that 6x becomes 0 and h squared becomes 0, and therefore our first derivative becomes 6x squared. Now, I want us to find the first derivative of this one. I'll give you 4 minutes to evaluate the first derivative of 1 over x using first principles. Right, welcome back. I hope you have had a good time doing this one. If I can check, our function is f of x is equal to 1 over x. Our f of x plus h becomes 1 over x plus h. Now we got that. Let's substitute into our function. I know some attempted to substitute into the limit h tending to 0 of 1 over x plus h minus 1 over x over h. So that our work looks a bit organized, I'm avoiding this over because we end up losing one of the denominators there. Hence, I've written that one as divided by h, because we know that the fractional line means division as well. From there on, I have introduced a bracket so that I simplify what I have. The LCD of x plus h and x becomes the product of x and x plus h. And then from there on, we know that x plus h into the LCD, x remains, and that x multiplies the numerator 1 there, and we get x minus x into x. We will remain with x plus h, which multiplies the numerator 1, and we get x plus h. Take note of the bracket there. The negative sign is going to affect everything there. When we simplify this, we'll get negative h over the LCD, which is x multiplied by x plus h. I will now change the division sign to a multiplication sign, and then I will invert the divisor, which is h, and it becomes multiplied by 1 over h. I'm able to see that this h is the same as that h, and that will give my answer as negative 1 over x plus x all over x bracket x plus h. That's my denominator. My numerator is negative 1. I now evaluate my limit, and my limit will be negative 1 over x squared. Now, that's the first derivative of 1 over x. It will be given by negative 1 over x squared. I will give you a chance to do these ones later on. I quickly want us to move on to this part. Now, we have to look at the notation that we are going to use. So, we determine the derivative of function. We also say that we differentiate the function. As we have been doing, we're finding the first derivative from first principles, and the process of finding the derivative, it's differentiation. And you have seen that from first principles, we have worked with those functions, and we have seen what we're able to see. The notation now that we must know: if your function is f of x, the derivative will be given by f dash of x. If your function is given by y equals, it means the derivative will be dy dx equals. If your function is given by the expression, you will find d, for example, it means whatever expression you have inside the brackets, you are deriving it with respect to the letter that you have as the subscript down there. For example, if the expression is in terms of x, it means you are finding the derivative with respect to x. For this one that I've written here, it means you are finding the derivative with respect to t. And also, if you are given an expression d dt, it means whatever you have in brackets, you are finding the derivative with respect to t. Now, we must be able to use the rules of differentiation. You will find out that if you are having two functions in the same expression, you have to find, for example, f of x plus minus g of x. You find the derivative of the first expression followed by the derivative of the second expression. Then you are able to find the derivative. Now, let's just summarize what we just discovered. Our function was f of x is equal to 5. The first one that we did, the derivative was f dash of x is equal to 0. Let's now find a way. In case a question did not say do it from first principles, we have to find a way of how we can find the derivative. For example, if the question is 1 mark, definitely you don't need to use first principles unless the question has stated that use first principles. You will find out that this is a constant. So if our function is a constant, you will find out that the derivative will be equal to 0 as illustrated on the rule on the left hand side. We did the derivative f of x is x plus 3. We found we had f of x is equal to 3x plus 2. We did the derivative and we found out that f dash of x was 3. So we can try and check what happened. We had our coefficient of x as 3 and we have our derivative as 3, but we no longer have the variable x. Let's check what could have happened. You will find out that if our function is ax, our derivative becomes whatever is the coefficient of that x. We move on to the next one. We discovered that our f of x was given by 2x cubed and our derivative was 6x squared. Now, what can we deduce from there? We're able to see that for us to get this 6, we said 3 times 2, we got the 6, and then the exponent of 3 was reduced by 1, which is the same as 3 minus 1. So we can generalize and say the rule is given by a. If f of x is a times x to the power n, then it becomes n times a times x to the power n minus 1. We are able to see that. Then if our f of x is 1 over x, we can use the laws of exponents to change that into x to the power negative 1. And then from there, we are able to find the derivative as negative 1, x to the power negative 2. We know that this is the same thing. That one is a negative exponent and this one is a positive exponent. What rule did we use? You are able to realize that if our exponent is negative, still it multiplies our coefficient and then the exponent is reduced by 1. Now, I will give you 1 minute to evaluate the derivative using the rules now. Right. This example is a straightforward one. We have y is equal to 3x squared minus 6. Remember the notation I talked about? So, for us to evaluate the derivative, because our function is in terms of y, we are going to first of all write dy dx. Then we apply the rule. The exponent is 2. We multiply 2 by 3, we get 6. X, our exponent is 2 minus 1. Negative 6 is a constant. We know that the derivative of a constant is 0. And we will get our answer as 6x. You are able to see that. In an exam situation, this one will only be 1 mark. If it comes, you are not using first principles, but it just says find the derivative. You are using the rules of differentiation. Now, example 2, I'll also give you 1 minute to quickly evaluate the derivative using the rules of differentiation. Right. You will realize that our y is given as 3 minus 2x minus 4 over x squared. Now, there's some manipulation that we need to do first before we are able to find the derivative. We can write this as y is equal to 3 minus 2x minus, we write this as a negative exponent. Our coefficient becomes 4, and that becomes negative x to the power negative 2. Now, remember, I can write this as negative 4 times 1 over x squared, so that you are able to see that 4 is not always pinned to this x squared. As a fraction, 4, I can write it as negative 4 over 1 multiplied by 1 over x squared. And I know that 1 over x squared, as a negative exponent, it becomes x to the power negative 2, and still it will give me that expression. To evaluate the derivative, it becomes dy dx will be equal to 3. It's a constant, it will give us 0. And then our exponent here is 1. 1 times negative 2, we get negative 2 to the power. 1 minus 1 will give us 0. And x to the power 0 is the same as 1. Negative 2 times 1 will give us negative 2. And then my exponent here is negative 2 multiplied by negative 4. That should give us positive 8. And then from there, my exponent x becomes negative 2 minus 1. Our exponent becomes negative 3. And this should give us our answer. In an exam situation, this question will have 3 marks for changing that to a negative exponent. Negative 4 over x squared, we change it to a negative exponent. And then the derivatives. So this question will have 3 marks there. You can see what has happened, and we get our solution. Sometimes you may be asked to leave your solution as a positive exponent, but it's not a requirement. I know when we are being taught, we are taught that we should leave our answer as a positive exponent, but don't worry about that. You should just evaluate the derivative. If you leave your exponent as a negative, you will not be penalized unless the question says leave an answer as a positive exponent, then you must have to change it. But if not, just leave it as a negative exponent, it's okay. We move on to example 2. I'll give you 1 minute to find the derivative using rules of differentiation. 1 minute, let's quickly look at it. Right, I hope we have managed to work on this one. This one requires us to know our laws of exponents and sets. Now, to evaluate this one, we need to first of all make sure that our variables are in exponential form. So I can write my f of x square root. I know that square root is x to the power 1 over 2 plus 1 over 3 x to the power 1 over 2. Remember, I'm not evaluating the derivative. I'm just manipulating for now. So f of x will be given by x to the power half plus 1 over 3. I'm now writing this as a negative exponent. Remember, as I indicated, I can write this as 1 over 3 multiplied by 1 over x to the power half. These, I can write them as two separate fractions. This 3 is not pinned to the x or square root x. So from there, I can now write 1 over x to the power half as a negative exponent. It becomes x to the power negative half. From there now, I'm able to evaluate my derivative. My exponent is half there, so it means half times 1 will give me that x to the power negative half. Negative half times 1 over 3, it will give us negative 1 over 6 x to the power negative half minus 1 will give us negative 3 over 2, and that becomes my solution. So in an exam situation, again, for changing this, you will get 1 mark for the first step, changing this to a negative exponent, and then the derivative of the given terms. It could be 4 marks in an exam situation. We move on. You are able to see the solution there, the typed one. Maybe my values and my handwriting is not that nice, but you can see that one is a bit nicer. Now, we have to find things decided to move there, but let me write it down. The expression is you have to find d of x, given that we have 1 over x squared minus x to the power 12 plus x to the power 5 over x to the power 6. Let's quickly find the derivative using the rules of differentiation. I will give you 2 minutes to work on this one, as you need to do some bit of work before you can work on it. All right, I hope you have managed to work with this question. First of all, we can see that this does not look nice. We must try and make sure we have a linear expression before we can apply the rules. So we are supposed to find the derivative with respect to x. So I will rewrite this as d of x. The first one, I'll write it as x to the power negative 2 minus x to the power 6 is affecting the whole fraction. Now, I will show you using 2 ways. So the first one, I know that 1 over x to the power 6, I can write this as x to the power negative 6. Then I put x to the power 12 plus x to the power 5 inside another bracket so that I'm able to multiply each of the given terms as exponents. So this will give me x to the power negative 2, x to the power negative 6 times x to the power 12. I add the exponents, negative 6 plus 12. This will give me negative, because of the negative sign, x to the power 6. And then x to the power 6 times x to the power 5. This will give me, because of the negative, this becomes negative. And I'm able to see that negative 6 plus 5, because my exponent there is 5, will give me x to the power negative 1. Now, as you can see, as I'm manipulating, the d of x is still written. I'm not evaluating the derivative. I am manipulating the expression so that I'm able to use the rules. Now, when I use the rules, I no longer write the d because now I'm evaluating the derivative. Hence, I will not write the d of x. So this will give me negative 2x to the power negative 3 minus, my exponent there is 6x to the power 5. Negative and a negative, this will give me positive x to the power negative 2. And that will be my derivative. In an exam situation, 4 marks. 1 mark for the manipulation up to that stage. 1 mark for each of these terms that are correctly derived. That will give us 4 marks. You can see the way I've worked out the solution there. It comes out well. And we are able to get our solution as that. Now, I'll give you about 6 minutes. Maybe 6 minutes is too short. I'll give you 7 minutes to try and answer 8.1 and 8.2 and 8. You answer all the questions in, let me give you 10. Yeah, in 10 minutes, work out the whole question. 10 minutes. I hope we have managed to answer this question. Now, the first question requires us to use first principles. Remember, you check the definition of first principles. You evaluate f of x plus h first, then you substitute into the definition. Now, there we are. We evaluated our f of x and we got that. We'll get 1 mark, for evaluating f of x plus h. We then simplified. You can see this is our numerator on our definition. We have done the substitution and the simplification. We are then writing down the definition, and after writing down the definition, we substitute the simplification. We then factorize our h, common factor, they will cancel each other there. Then we are left with the limit as h approaches 0 as 2x plus h, and then we will get our derivative as 2x. You are able to see how the 5 marks are distributed there. It was 5 marks. I hope you enjoyed doing that one. 8.2, we are given our function as y is equal to 3x cubed plus 6x squared plus x minus 4. This one, we are just supposed to use the rules of differentiation. You can't use first principles there for 3 marks. We just use the rules. So you will realize that our function is given as that. So to find the derivative, our exponent is 3. 3 times 3 will give us 9. And our exponent becomes x squared. So we'll have 9x squared plus 12x plus 1. So for each of these terms, you are getting 1 mark in an exam. The question is 3 marks because you did not have to manipulate anything there. Then the next question, it's 8.22. This one looks a bit of a challenge. So as I indicated, some of the questions you need to manipulate them before applying the rules. And you are told there that your x cannot be equal to 1. So that it's a hint that somewhere, somehow, we have to divide and have a fraction. And that fraction is going to have a denominator somewhere. So let's quickly do the manipulation. If I check on my numerator, I see that y is a common term. I'll have x minus 1 equals. If I check on the right hand side, 2 is a common factor. I will remain with 2x is a factor. I'll remain with 2x, then bracket, I'll remain with x minus 1. From there on, I'll have my y is equal to 2x into x minus 1, all this over x minus 1. From there on, I'm able to see that x minus 1 and x minus 1 is going to give me 1, and then I'll remain with y is equal to 2x. Then can I now find my dy dx? And this will give me my answer as 2, 4 marks. Let's check how the marks are distributed. You have seen the first step. We get our y as 2x. Then we do the derivative. For making your factorization, left hand side 1 mark, right hand side 1 mark, getting your y as 2x and then the derivative there as 1, you are able to see the mark distribution there. I think we can quickly copy this one and try to work it out. Let's jump the first part. We have done the first principles and we just do 7.2 and 7.3. In 1 minute, we should be able to mark this one. I'm giving you 1 minute. Let's quickly try it. Okay, now we jumped 7.1. 7.2, we are simply going to find the derivative. We are saying our y is equal to 4x to the power 8 plus, we change that one, it becomes x to the power 3. We know that square root is power half, ne? So we can write this as y is equal to 4x to the power 8 plus x to the power 3 over 2. Then we evaluate dy dx, and this will give us our answer as 32x to the power 7 plus 3 over 2x to the power half. So we will get, for changing the square root sign to exponential form, and then for each of the two derivatives we get our solution. 7.3, we have our y as ax squared plus a. To find dy dx, you are finding the derivative with respect to x. That one will give us our answer as, we'll get 2ax as our solution. Because our exponent is 2, we multiply that by a, we get 2a. The exponent reduces by 1 to get x to the power 1. And as you can see, there are two variables there. So we can still find the derivative with respect to a, and that one will give us our dy dx. So we must first of all do the manipulation. We'll get our y as a is a common factor. We remain with x squared plus 1. So dy dA means we are finding the derivative with respect to a, and x squared plus 1 becomes the coefficient of this a if you are looking at it from that point. And we know that the derivative of a constant a will give us what we call our, so we'll have our exponent, in this case it's 1. 1 times a is going to be 1. A to the power 0 becomes 1, and we will remain with x squared plus 1 as the coefficient. Therefore, dy dA becomes x squared plus 1. So that will be our final solution for that question. Now, this is a question for homework. We can quickly take a picture of the homework, and then, because time is no longer on our side, the homework solutions, you were supposed to get them, but I will put them up at the end of the lesson as time is not on our side. Now, in summary, we must use function notation. You saw how we are able to evaluate f of x plus h. We should use first principles. We know the definition of first principles. F dash of x is given by f of x plus h minus f of x all over h. The limit as h approaches 0. We must know the definition and we should use it correctly to determine the first derivative. We use correct notation. You saw the expression. If the expression is y equals, the derivative is dy dx. For example, if the expression is in terms of x. If the expression is in terms of t, you are able to evaluate the derivative as dt of whatever you have as the expression in brackets. The differentiation rules, we're able to see them. If it's a constant, the derivative becomes 0. If it is a function with a monomial, the derivative is whatever is the coefficient of that monomial. And you saw as we did from first principles. Thank you for watching this lesson. Please keep safe and let's continue to practice social distancing. We sanitize, we wear our masks so that we protect ourselves from the COVID. And all the best for our paper 1 that we are going to write on the 3rd. Thank you.